Okay, hi everyone. This is Dan Barry in Silver Spring, Maryland. Welcome to this month's MAP webinar. The topic of the webinar is Understanding and Modeling Climate Extremes. We have 5 speakers. We actually have 6 speakers giving 5 talks. The first talk is going to be from Suzana, Camargo, and Kerry, Emanuel. The second talk will be from Chunzai, Wang. Third talk from Bosart. Fourth talk from Rong, and the 5th talk from Upmanu, Lall. The first couple of talks are on the topic of tropical cyclones, and the last 3 are on other extremes, both drought and precipitation extremes over the United States. Our first speaker is Suzana. So, Suzana, what I'm going to do right now is switch control, or I guess, Kerry, you're going to talk first?
I think we decided to do it that way. I don't remember why, but yeah.
All right. So, Kerry, I'm going to transfer control over to you right now.
Okay.
And I'd like to remind everybody on the phone while we're doing this to please mute your phones. I do hear some static and some background noise, so not everybody's muted. Kerry's the only person who should be on mute right now. Okay, so Kerry, do you see that share my desktop button on your screen?
No, I've got my own presentation up.
Oh, okay, so you're going to have to flip over to the WebEx program.
Okay, yes, I got it. I'll do that.
Great.
Okay.
All right, excellent. So whenever you're ready, feel free to start.
All right. Well, Suzana, Camargo, and I are going to talk about the effect of climate change on hurricanes, and I'll go for 10 minutes or so, and then Suzana will pick it up. Just to be sure that we're all on the same track, here is the distribution of tropical cyclones around the world over the last 60 years or so. Showing the well-known regions of tropical cyclones in the Atlantic, in the eastern and western North Pacific, in the southern hemisphere, and so forth. These are color-coded by Saffir-Simpson category. The Atlantic is an interesting place to look. Even though it contains only 11% of the world's tropical cyclones, it has far and away the best measurements. And what I'm showing on this graph are 2 quantities. The red curve is something called the Power Dissipation Index. It is based upon the so-called HERDAT, or best track data, and it's the accumulation of the cube of the wind speed of hurricanes over the life of their storms and over each year in the Atlantic. And it's a measure of the total amount of energy dissipated by hurricanes over their lifetime. That's the red curve. And the units are not units you'd be familiar with anyway, but if you look at the scale over on the right, you see that between the 1980s and the last decade, hurricane power has roughly doubled. So whatever the cause of these changes, that's a very large change, and it's of interest. Is this a natural climate oscillation? What's going on here? By the way, from the 80s to the present, we don't have any particularly serious problems with the hurricane data. Before about 1970, we start to run into problems. The other curve on here is simply the temperature of the tropical Atlantic, where hurricanes tend to form, averaged over the months of August through October. That's the blue curve, and the scale is red over on the left. And you can see a reasonably high correlation between these two. In fact, the R-squared is well over 0.8. They're highly correlated. We have reasons to think that they should be, although the magnitude of the change in power dissipation for a small change in SST has taken everyone a bit by surprise. Now, what's causing one thing that you might ask, given that there appears to be a relationship between hurricane power and sea surface temperature, what causes the sea surface temperature to change? Well, on this graph, what I've done is to plot exactly the same sea surface temperature curve that I showed the last graph in blue, except that it has been smoothed over 10 years. It's a 10-year running average. That's the blue curve. And the long-term mean has been subtracted, so it's zero-centered. And the green is the August through October northern hemispheric surface temperatures. That's the whole northern hemisphere, including land. And I would argue that the great similarity of these 2 curves strongly suggests, although it does not prove, that the Atlantic is simply doing the same thing as the hemisphere as a whole, and is not doing anything particular. Now this, I have to emphasize, is the summertime tropical Atlantic. We're not talking about the far North Atlantic. We're not talking about winter. The tropical Atlantic in the summer follows the northern hemisphere. So if we can understand why the northern hemisphere did this seesaw that you clearly see on this graph, we would be perhaps ahead of the game. Now, we're going to back off one more step to the globe, which is in this slide. I think many of you have seen this before. The black curve at the top of this slide is the global mean temperature relative to its value in the year 1900. And the brown curve with the gray shading behind it is an attempt by a suite of global climate models to simulate the climate record of the 20th century. And you can judge for yourself how successful or unsuccessful those models have been in that endeavor. There's also interesting questions about the extent to which the models may or may not have been tuned to do this. But in any event, given that curve, it's not so difficult to deconvolve from the models what contributed to those changes. Of course, there's natural chaotic variability, but the forced changes are shown by the colored curves at the bottom of this graph. And so up till about 1960, there were basically everything that you could think of might be contributing to the forcing was contributing in some way, and these include solar variability, changes in the incidence of volcanoes, which tend to cool the climate, greenhouse gases, and sulfate aerosols, which are anthropogenic and intend to have a cooling effect. So we would say that basically all of these things were active up till 1960. The cooling from the 50s to the 70s is probably responsible in the models for the leveling off or cooling of the overall climate from the 50s to about the 70s. But in the last 30 years, particularly, the greenhouse gases seem to have been the dominant agent. Now, we're going to start with the globe, and we're going to back off again to the northern hemisphere, and this is work I did with Mike Mann a few years ago. The red curve here is the global mean temperature relative to some long-term mean going back to about 1870 or so. And the blue curve is the tropical Atlantic sea surface temperature, which, remember, is similar to the northern hemisphere. The aqua curve is an estimate of sulfate aerosol radiative forcing beginning essentially zero at the end of the 19th century and then going negative on its effective temperature. And Mike and I simply asked, can we explain the difference between the globe and the North Atlantic by the sulfate aerosols? And now on this next slide, the red curve is just a linear combination of global mean temperature and aerosol forcing, and it lines up quite well with North Atlantic temperature. So our feeling, and Mike Mann, I might add, was the person who essentially invented the term Atlantic multi-decadal oscillation, but he and I both feel that the summertime tropical Atlantic is better explained by time-varying radiative forcing that just happens to produce a seesaw pattern. I would emphasize that two peaks in one trough or two troughs in one peak are not enough to establish any kind of cyclic behavior, but the notion that the Atlantic temperature is following a cycle is unfortunately widespread. Now, very recently, just literally last week, a paper appeared by Booth et al. In Nature, which tends to support the interpretation that a lot of the seesaw behavior is not due to a natural oscillation, although natural modes of the ocean may have played a role in the response, but to variations in radiative forcing owing to everything, basically volcanoes, aerosols, and so forth. So the top two panels show the distribution over the Atlantic of the direct and indirect effects calculated in this particular model of aerosol forcing. And what I think is very interesting about the right-hand graph is you can see that the aerosols that affect the tropical Atlantic, that is west of sub-Saharan Africa, really originate, for the most part, in North America and are carried around in the low-level winds into the equatorial Atlantic region. The bottom graph simply shows time series, detrended in this case, of aerosol optical depth and effective radius, where you can see the profound cooling effect that was present in the 60s through the 80s. So I think the evidence in the Atlantic is now fairly strong that one of the interesting climate signals was a suppression of tropical Atlantic temperature and correspondingly tropical Atlantic hurricane activity in roughly the 60s through the early 90s by a largely man-made influence, the sulfate aerosols, and the rapid increase in hurricane power that I alluded to earlier, the factor of 2, is maybe partially a greenhouse gas-induced phenomena, but may mostly be a recovery from the large aerosol cooling that we saw in the 70s through the 80s. Let me just very briefly turn to the Pacific, the northwestern Pacific in particular. What's going on there? Well, arguably that's the place where we have the second best data because we did do hurricane reconnaissance in the western North Pacific in the 40s through the late 1980s, and it contains roughly 40% of the world's tropical cyclones. Well, here is the tallied up power dissipation from western North Pacific cyclones going back to 1970 in red. I don't know why the scale got dropped off, but in the blue curve is just a Pacific Decadal Oscillation Index from the University of Washington. And you can see, I think by eye, a fairly high correlation. So I would argue, and others have before me, that what's happening in the Pacific is largely controlled by this Pacific Decadal Oscillation, whatever that is. I don't think there's widespread agreement on what it is. So the irony is that while there are many papers linking multi-decadal variability in the Atlantic to a natural oscillation, the evidence, I think, points more strongly to Pacific activity being controlled that way. This is just a map of the principal components that define the Pacific Decadal Oscillation. You've perhaps seen those before. So I'll summarize my part of this. I didn't say anything about this at the beginning, but tropical cyclones are important for society for a variety of reasons. One of the indicators is insured losses worldwide. Atlantic hurricane power has more than doubled since the 1980s. Atlantic hurricane power tracks summer tropical Atlantic Ocean temperature quite closely, and that seems to be controlled, that is the summer Atlantic Ocean temperature, mostly by radiative forcing, especially aerosols in the last 50 years and perhaps greenhouse gases in the last 30. But in the western Pacific, the activity seems much more closely linked to I hesitate to call it a natural climate oscillation because I don't know what it is exactly, but it's whatever people call the PDO seems to be linked to variations in that activity. So with that, I will turn things over to Suzana.
Okay, thanks a lot, Kerry. And as Kerry says, we're going to switch control over to Suzana Camargo, who's going to finish up the presentation. Suzana, you're on the phone?
Yes, I am.
Great. So I just switched control over you. Do you see the Share My Desktop button?
Let me see. Yes, I am here. Can you see it?
Yeah, absolutely. So if you just go full screen, great.
Okay, so this is a project that we started recently, and it's a collaboration with Kerry, Adam, Sobel, Tim Hall, and Jim Costin. And what we want to look at is, can we say anything yet about tropical cyclone tracks and climate change? So first we want to see if we can identify significant change, and then look if there are significant changes, what are causes of this change, and then look if there is any predictability for this track change. So we just started that, and the methodology that we're using for this project, we're using a cluster analysis as a way of diagnostic this track change. And we're looking at different types of tracks for dynamical models from CMIP5 and different other model simulations. And then we're going to look at tracks from the statistical dynamical downscaling that Kerry has developed, and also from tracks from purely statistical models from Tim Hall. So I'm going to show why we're using this method. So this is a paper that I wrote with Jim Costin a couple of years ago, and in the left panels, you can see the tracks of hurricanes in the Atlantic, tropical cyclones, and you can see that you can separate these clusters in different types of tracks. So this top cluster, you have storms that are more of subtropical origin and have a lot of landfall in the northeast coast of the United States. And then we have cluster 2, we have more Gulf of Mexico cyclones. And then we have 2 different tropical, deep tropic forming cyclones in cluster 3 and cluster 4. And then in this work, we look at what the environmental factors are related to any of these, to each of these different types of tracks. So we started looking at a few CMIP-5 models in the North Atlantic. I started with these 4 models, GFDL, Hadley, MPI, and MRI, and I look at the historical and the 2 warming scenarios. So the first thing we want to look is how well these models are able to reproduce the observed tracks. And the first answer is not that well yet. So you see on the left panel, this is the GFDL historical run. On the right is the Hadley GM2. And then we have the NPI and the MRI models. And all these models are not active enough. And of course, all these things are very sensitive to the tracking routine that you're using. I'm using one that I developed many years ago. But here, all these models are tracked with the same exactly tracking routine. So whatever dependence there is in the tracking we here is uniform among these models. So the one that seems to be doing a best job here is the NPI model. So I'm going to show this is my first result with that. You see, that's the only one has both tropical forming and some recurving and more this subtropical kind of forming storms. While GFDL is only this storm that formed in near Africa. And the MRI just basically just has subtropical kind of storm. So if I apply the same cluster analysis as I showed for the observations to the NPI historical track, then I'll have similar kind of results with 1 cluster forming the deep tropics, 1 subtropical cluster, and 1 in the Gulf of Mexico. But I do not have this kind of cluster type of track in the observations. The subtropical ones forming more in the eastern part of the basin. This is something that this model makes that doesn't seem to exist in observations. And also we have had in the observations 2 types of tracks in the deep tropics, one for more forming more the eastern part of the basin, one to the middle of the basin. And this model doesn't join the middle part with the Gulf of Mexico track. So we already see clearly very many biases in the model, even the best one that we could find from these 4. And now if I do this analysis using the historical and the warming RCP 4-5 scenario. So here in blue you have the tracks of the historical, and in red I have the tracks of the warming. And the percentage of tracks in each of these clusters is given on top. So you see that the top cluster, you have a very similar percentage of tracks for both historical and the warming, and the same thing with the bottom left. While there is an increase in this subtropical type of tracks for this model in the warming case, and a decrease on the deep tropics when I'm warming. And we have to look if this is statistically significant or not. But when I look at a more extreme scenario, the RCP 8-5, this kind of result is even more extreme. So there is a much higher increase in this subtropical track in this model for this more extreme warming, and a higher decrease level in the deep tropics for this model. So now we're going to apply the same techniques to many more models and see if this is result that we're having is a specific of this model or we can identify in other models. And we want to also examine what's the optimal way to apply this cluster analysis to multi-models and multi-scenarios. That's something we have technique. And then we want to look at for other regions, Western Pacific, Southern Hemisphere, and work on the other types of tracks, the statistical dynamical and the statistical tracks for both kinds of conditions. That's all I have.
Okay, thanks a lot, Suzana, and thank you, Kerry. That was an excellent talk. I ask everyone to please save questions until the end of all of the presentations, so perhaps you want to consider writing it down so that you can remember until the end. We're going to move on now to our next speaker, who's Chunzai Wang. Chunzai, are you on the phone?
Yes, I'm here.
Okay, great. I'm going to transfer control over to you right now.
Okay.
Okay, great. I can see your screen.
Okay. Let's start here. Hi, everyone. I'm Chunzai Wang from Miami, and today I will talk about how climate change hurricane landfall. And first, we take a look at why the TC move northwestward in north hemisphere. Basically, we have two effects. First one is the so-called beta effect, and the second one is the environmental steering flow. We take a look at the first beta effect first. And this is a simple equation is the vorticity equation. And the first term is vorticity tendency term, and the second term is advection term, and the last term is the beta effect. So if we have a hurricane in north hemisphere, because the hurricane has vertical flow, so in east part of the cyclone, and the beta term is this last term is negative. So the vorticity tendency term in east part of the hurricane is negative. However, in the west part of the hurricane, vorticity tendency is positive. So the hurricane moves westward. And this slide we just show beta effect will produce the positive vorticity in west part of the hurricane and the negative vorticity in east part of the hurricane. So this vorticity pattern will set up so-called secondary circulation, which in red color. So this secondary circulation will move hurricane northward. So we have westward movement, we have northward movement, so combination result is TC move northwestward. So next we take a look at the TC steering flow. So actually we can compare a TC track with a leaf in the stream. Where the leaf going depends on where the stream flow. Similar situations where hurricanes going depend on the atmosphere circulation. So in North Atlantic Ocean, a major feature is the North Atlantic subtropical high, and people call the NASH. So the NASH play an important role, especially the water controlled NASH. In our study, we focus on warm pool. And actually, in 2001, we published in this paper, we named West Hemisphere warm pool. We defined the SIT anomaly larger than 28.5 degrees as a warm pool. So by this definition, warm pool has two parts. One is in East Pacific part, which is starting in March and the peak in May, decay up in June. At the same time, Atlantic part warm pool starting to develop and the peak in September. And in our study today, we're talking about we focus on Atlantic part warm pool, so we call Atlantic warm pool. Basically, we have Atlantic warm pool has two ways to affect the TC track. First is the warm pool variability will change TC genesis location, then TC track. The second one is warm pool variability will induce atmosphere circulation change, which then changes the TC track. we first take a look at the TC genesis location and the warm pool. So basically here, I show here, this slide is composite. So over last 40 years, we choose 10-year large warm pool, we choose the 10-year small warm pool. Then we make a composite. The top panel shows large warm pool case, low panel shows small warm pool case, and the shading, the sea surface temperature, and the dot represent the TC genesis location. So this slide actually had 2 points I want to mention here. First, we take a look at number of the TC. So you see that for large warm pool we have 126 TC, and for small warm pool we only have 79 TC, which suggests large warm pool will increase the number of TC. And the second point is the location of the TC genesis location. We compare small warm pool, large warm pool case, TC genesis location shift eastward. So we have more TC form in East Atlantic Ocean, which means the large warm pool will shift eastward of TC genesis location, which will decrease landfall possibility. Now next, and this is simple table. We look at hurricane form in main developed region during the last 40 years. We choose 10 large warm pool year and 10 small warm pool year. So here is the number hurricane for large warm pool. We have 31. For small warm pool, we have 13 hurricanes. So again, the large warm pool will increase the number of hurricanes. Then we take a look at the landfall hurricane. So large warm pool we have 7, and the small warm pool we have 5. The ratio is 1 is 0.23, another is 0.38. So basically, large warm pool reduce issue of U.S. landfall by 14%. And next, we take a look at the TC steering flow. Again, we make a composite because we use last 40-year observation. We choose 10 left panel, 10 large warm pool year and 10 small warm pool year. Then we calculate the composite of the TC steering flow anomaly. First, we take a look at large warm pool case. In large warm pool case in the southeast U.S. and the Gulf of Mexico, the TC steering flow is southeastward, and over West Atlantic Ocean, TC steering flow is northeastward. So this kind of steering flow pattern is where steer hurricane away from U.S. In other words, large warm pool year is not favorable for hurricane to make landfall in U.S. And the opposite situation is true for small warm pool. Small warm pool year, small warm pool is favorable for hurricane to make landfall in U.S. And then this slide shows the steering flow in neutral warm pool year. What mean neutral? It means normal. Warm pool is not large, warm pool is not small. So you see the during neutral warm pool year, steering flow is very, very small, which is suggesting warm pool variability is very important for the steering flow change. Then we use the TC track density data to take a look at the relationship between warm pool and the TC track. So what we did, this figure here is the regression of TC track density onto warm pool index. Contours regression coefficient, and the shading means the above 95 significant level. So you see that this regression is positive value, which means large warm pool will increase the TC activity overall, which is consistent with our early result. And the second point here is that you see the regression that have 2 maximums. One is over the Atlantic Ocean, one is over the intra-American Sea region. So this maximum value is basically due to the deform locally. So to confirm that, we remove the TC form in the AS region, then recalculate the regression. So basically, this maximum regression is gone. And the last point I want to emphasize here is we see the regression, orientation of the regression is from south to north, which suggests one pool is favorable for northward TC track, which means over the open ocean, is not favorable for hurricane make landfall to U.S. We also take a look at the impact also on TC track. It's a similar calculation, but in this case, the regression is onto the medium sleigh index. So you see the regression is negative everywhere. What this means? This means La Nina is favorable for hurricane to make a landfall. And we also calculate the impact of NO, North Atlantic Oscillation. So you see the regression map is not significant, which means NO has later effect on the TC track. And we also take a look at AMO, Atlantic Multi-Decadal Oscillation. So you see the pattern, this pattern are similar to one pool pattern I just showed you earlier. So this suggests the influence of AMO operating through the one pool induced mechanism, which is consistent with our 2008 paper. It's the observation. We also use a numerical model to test some result. The model we use here is the NCAR atmosphere GCM model. And basically, we perform 3 group ensemble run. The control run, large one pool, and small one pool. Control run, in the control run, the model is forced by climatological activity globally. And for large one pool ensemble run, in one region, we use large one pool composite activity force model. And outside of the one pool and force is the climatological activity. The similar situation is for small one pool. So basically, left panel shows sea level pressure response for the control run. So basically, the model is able to simulate the NASH, North Atlantic subtropical high. And the red panel shows the sea level pressure difference between the large one pool and the small one pool model run. So basically, the response is negative. Sea level pressure is negative, which have a negative value in the one pool region, also the negative value over the northeast Pacific. So it's basically the large one pool where they weaken the NASH, also push NASH northeastward. And here is again the model result, which shows TC steering flow and the NASH. The left panel shows the TC steering flow between large one pool and small one pool. So basically, the pattern is similar to the observation I showed you earlier. The latter two panels show the sea level pressure in large one pool run and the small one pool run. So basically, for large one pool run, as I said earlier, the one pool effect is reduced and pushes one pool to northeastward. For example, if we take a look at the 1021 millibar contour for the large one pool model run, this 1021 the contour is over northeast Atlantic Ocean. However, for the small one pool cases, the contour across the whole North Atlantic Ocean reach east coast of U.S. So, if a hurricane form in the May-developed region like here, then this kind of atmosphere circulation pattern will favor hurricane make landfall in southeast U.S. However, in other cases, for large one pool case, the atmosphere circulation pattern is make the hurricane move northwestward, then recurve northeastward without making landfall to U.S. And next, we take a look at 2010. 2010 is a very unusual year. 2010 we have a busy season. We total have 19 storms and we have 12 hurricanes. And if we count the hurricane form in the May-developed region, we see the no hurricane make landfall in 2010. The question is why? So we take a look at the the Pacific and Atlantic Ocean in 2010. So top panel shows the sea surface temperature in hurricane season, and low panel shows the SLT anomaly over Pacific Ocean. So Atlantic Ocean in 2010, warm pool is extreme largely, very large, and same time the Pacific Ocean is La Nina condition. So as I said earlier, so this kind of large warm pool La Nina will increase the number of the hurricanes. This is why 2010 hurricane season is very busy. However, as I said earlier, large warm pool is unfavorable for hurricane making landfall, and La Nina is favorable. So next we take a look at the TC steering flow in 2010. You see that the TC steering flow in 2010 is similar to the observed composite I showed you earlier. So in southeast U.S., the steering flow is southeastward, and over the west Atlantic Ocean, the steering flow is northeastward. So this kind of TC steering flow will carry a hurricane away from U.S. This is why no hurricane making landfall in 2010. Yeah. Basically, the summary. So both large warm pool and La Nina can increase the number of hurricanes. However, the large warm pool is unfavorable for hurricane to making landfall in U.S. The mechanism is two. One is the large warm pool will shift the TC genesis location eastward, so hurricane decrease the possibility for hurricane to make landfall. And second mechanism is large warm pool will induce atmospheric circulation and the TC steering flow, which is steering hurricane away from U.S. coast. This is then La Nina is favorable to make landfall, and El Nino is not favorable. The last conclusion summary is about 2010. 2010 the busy season and no hurricane making landfall, and 2010 is a large warm pool year, also is La Nina year. So this result suggests that in 2010, effect on large warm pool is larger than the La Nina effect. So net result is no hurricane making landfall in U.S. So basically, last two slides I want to show is okay. How about 2011? Last year. Last year is similar situation. Actually, we have 19 storms and 7 hurricanes. So basically, you see the most hurricanes move northwestward, then they curve to the northeastward. And 2011, Atlantic Ocean's warm pool is also large. So basically, 2011 is also consistent with the result I show you today. Okay, I stop here. Thank you.
Thanks a lot, Chunzai. It was excellent, very interesting talk. Our next speaker is Lance Bosart. Lance, are you on the phone?
Yes, I am.
Okay, great. I'm going to switch control over to your computer. Okay, great. I can see your desktop, so...
Good to go?
Yeah, just maximize your slideshow, so it looks like the button right underneath where your mouse is right now.
It's maximized. I've got full screen here.
Great, okay, we can see that too.
Okay. This is really a story about the subtropical jet and its impact on extreme weather over the U.S. and the Americas. And with my co-authors, Heather Archibald and Jay Kodira, former Albany PhD student, Naval Postgrad School and NOAA Esrol respectively, and new faculty member at Albany, Andrea Lang. Okay, so I wanted to do here to illustrate the role of the strong North Pacific subtropical jet as a crucial antecedent to the Midwest cyclone of late October of 2010. Then look at the tropical and extratropical influences on the intensification and elongation of the subtropical jet prior to the event, then provide some context that extreme weather. All right, so first a few statistics. This cyclone produced a record-setting central pressure of 955.2 hectopascals in Bigport, Minnesota on October 26th. And it broke the record set by the Cleveland Superbomb from 1978 by about a couple of millibars, but this, of course, was further north. If you normalize by latitude, probably not the same. But the strong sea level pressure gradient resulted in widespread area of 55 to 65 knot winds, and there was a long-lived severe squall line and some tornadoes out ahead of it associated with a separate disturbance that was all part of the same weather system. The impact of the event is seen across the country. A lot of warm temperature records on the south side of the subtropical jet. There was a atmospheric river ahead of the storm on the subtropical jet. It impacted Northern California. And you'll see that there's not a lot of snowfall records up and through here in the little or magenta flakes and through here, but there were some rainfall records. So pretty much the whole country shared in the bounty of weather records that week. That was a high-impact event. All right, let's look at some of the antecedent conditions. Go back 12 days on that, 14 October, this red satellite imagery. There's the subtropical jet. You can see coming out of this Bay of Bengal disturbance, which I think should have been a TD, but was never named one in there. But the outflow from that disturbance was helping to drive the subtropical jet through here. TC Megi, which plays a role subsequently, is still relatively isolated from the mid-latitude flow this early on. Now, if we go forward 6 days to the 20th of October and look at a dynamic tropopause map, potential temperature is shaded according to the scale down there. The transition from blue to red, the cool colors to the warm colors, marks the axis of the subtropical jet and through here. The shaded contours on below are the layer mean, like out here, layer mean relative vorticity. So you can see there's a cold pool up here, cold pool number 1, trailing front out of it, and that's going to be intersected by Megi back here. There's TD Chaba, which is not going to play a role in through here. And there's a downstream anticyclonic wave-breaking event over the U.S., which is important as an antecedent because there's no real cold air in place out ahead of it. AWB referring to anticyclonic wave breaking, and the little red X is where there are disturbances in the dynamic tropopause. At the same time of that image, if you look at a satellite, you've got Kerry, which was, depending upon whom you believe, was a Cat 4 or Cat 5 at landfall in Miramar. No impact on the subtropical jet downstream. Megi now, you can see, is having a major impact on the subtropical jet. TD Chaba, no impact. Soon to be Tropical Depression 17W will play a role. The TC-TD interaction is correct if you're going to make a 10-day forecast. In another 24 hours later, if we look at a simple IR picture here, you can see the plume outflow from Megi is all the way almost to the west coast of the United States. Open cellular convection up here with the cold pool. First warm pool is over North America. The second pool outflow from Megi is coming, and then another eruption is coming out and through here. So I'll look at a cross-section along this line and look at trajectories ending at those 3 points and through here, which goes right, if you look at this image over here, at this time of sea level pressure, solid, thickness, 1,005 thicknesses in the blue dash to red dash, change over at 540 decameters. Water is through here, but if we look at a cross-section through there, you can see there's a nice tropopause fold in the process of developing along the subtropical jet. These are the endpoints of the 3 trajectories I'll show you in a minute. But note how high the dynamic tropopause is out ahead of this thing on the warm side, above 150 millibars. You can get a tropopause fold. You don't necessarily need a cold trough from high latitudes, but a lot of warm air from tropical disturbances bumping up against the subtropical jet and advected northward will produce a trop fold, and that's what happened in this case. Now, if you look at where the air comes from at these points in through here, the green and the red parcels start in the tropical boundary layer and over this period, Megi moves from here to here. They start in the bottom boundary layer and rise to about 11,500 meters. So you're getting deep ascent of air in the tropical boundary layer on the forward side of Megi that's up at subtropical jet level to help define that bariclicity. And then you've got on the other side, in the drier side, without much net vertical displacement, you've got a trajectory coming on the south side of the Tibetan Plateau all the way from Africa to define that area. And again, at that, what you're seeing here, there's the subtropical jet outflow all the way to the North America. Chaba is isolated. E17 is getting in position here. Forwarding to 12D and the 24th at this time, the subtropical jet axis and the cold pool has reached western North America. You can see the open cellular convection through here. So this is ready to come in. This amplification out here is associated with the remnants of TD17W, which is helping to produce some ridging here, which is accelerating the trough and through here and the approach of the subtropical jet to western North America. So if we summarize just the effect of the tropical disturbances on the subtropical jet, we have 5 things here. Bay of Bengal helped to strengthen the subtropical jet initially over Southeast Asia, likely TD string. Giri, which carried in the Cat 5 in the Joint Typhoon Warning Center, moved northeast to Myanmar but did not influence the subtropical jet. Megi Cat 3 helped to strengthen the subtropical jet over West and North Pacific and drive it eastward. Chaba, which maintained TD status, moved west-northwest but did not influence the subtropical jet. TD17W, which is 30-knot max sustained wind, provided moisture for low-level frontogenesis and deep ascent along the subtropical jet. 5 different disturbances, 5 different outcomes, all these conditional probabilities if you're thinking in terms of a 1 to 2 week forecast to try and get the interseasonal variability right. All right, so now let's look at the cyclone evolution itself. So these are maps centered on North America. There's an inset up here on the left of the dynamic tropopause map. 4, sea level thickness, sea level isobars every 4, it's solid.
Lance, I'm sorry to interrupt, but I can hear somebody typing on the line. Would everybody please make sure that their phones are muted? Thank you.
Let's see, okay. Thickness, red, first variety is 546. Here's the original storm that formed on the subtropical jet and the outflow from Megi, and starting to fill now off the west coast of North America, and a new storm is going to go on. What I want to point out to you, here's the subtropical jet. That's in here. This is 90 to 100 meters per second. It's starting to make its way onshore. But note the total absence of any cold air. There's not even a 540 thickness contour to be had over the U.S. This is the antecedent disturbance out here with this weak PV anomaly up here east of the mountains, which was associated with the severe weather I showed you before. Go ahead 24 hours. You're only 30 hours before the record low in through here. And note, again, the subtropical jet is coming onshore. The Lee cyclone is developing in through here in a thermal ridge. The absence of any cold air continues to be quite noticeable. And then by 24 hours later, at 12D to 26, now you got a 968 close contour. Of course, 6 hours later, you have the very deep 955 storm in through here with a strong subtropical jet coming in. Absence of any great cold outbreak behind it. Now, look at these 3 points here. Where does the air come from? The blue and the red come from the tropical boundary layer. The red comes from the TD17W, which moves westward, then northward, turns anticyclonically, and then ascends. The blue comes from the vicinity to the east of Megi, out through here, and also ascends from the boundary layer to 9,500 meters. The green came from all the way across northern Russia, down across from the higher latitudes, and subsided a bit, and they all joined together here near the tip of near where the dry slot is, and the tip of the moistest air at that particular time. Another issue, if you look at the Q vectors, 700 millibar flow, contour is blue is 700 millibar height, dashed red is every 3 degrees C isotherms at 700 millibars. Q vectors are indicated by the orientation then. So the shaded red, warm colors are forcing for convergence and ascent. Shaded cool colors are forcing for divergence and sinking motion. 36 hours before you have a deep, deep cyclone up here over northern Minnesota. Note the absence of Q vector forcing as your system comes in. 0 to the 24th, it weakens as it comes in like a classic system from the Pacific, but there is very little low-level baroclinicity to speak of for this system, and the Q vectors reflect that. This is a storm that's driven by the subtropical jet. And now you look upstairs and look at the 250 millibar wind. The solid contours are PV, standard PV units. The red areas are average vertical motion between 6 and 400 millibars. relative humidity is in the gray shading, and the irrotational wind vectors average between 2 and 300 millibars. These calculations were done with a half-degree GFS grids, by the way, in through here. What you see is the outflow from the developing cyclone, the irrotational wind there, and that outflow is here. It's helping to strengthen the PV gradient at the leading edge of the subtropical jet, advection of higher values of PV southwestward here, strengthening that gradient. But what I want to point out to you, 24 hours later, famous PV hook when you get a strong cyclone, which looks like a bigger, larger scale version of a hook echo with a severe weather event in through here. How does that form? It's the advection of PV by the irrotational part of the wind, the westward advection in through here, combined with the advection by the non-divergent wind, which I'm not showing you further to the south, that develops this dry slot, minimal PV, maximum PV coming in through here. Here's the hook. There's the little 8 value in through here. And the low PV air gets wrapped around on the backside of the system, strongly driven by the subtropical jet. So let's look at, say, some aspects to help try and put this in perspective. The variability of the subtropical jet, this is at 300 millibars, using that as a surrogate for subtropical jet. For 30 years, 79, 2008. This is the climatology over the course of 30 years of record, and this is the peak extreme values at the low end and the high end are shown here. So you can see the relative min, the sharp min in midsummer in July, and then the spin up, the autumnal circulation in here. The 200 strongest 300 hectopascal wind speed maximum for September, December are indicated by the small black dots because we're interested in that with respect to TC activity in the Pacific Basin in the fall. So here's the subtropical jet relative composite at 300 millibars for 200 events in here, those strong winds. And the statistical significance, the colored regions are greater than 95%. You can see anomalously high heights to the south, anomalously low heights to the north, 70 meter per second jet in through here. So in subtropical jet relative coordinates here, that's really very, very well defined. And then if we also look at the variability of the subtropical jet on frequency of west-north Pacific tropical cyclones relative to those strong subtropical jet days in box and whiskers plots here, so 95% and 5% of the edge of the whiskers in through here. And this is days relative to a strong jet day. What you can see in here is there tends to be a higher frequency of west-north Pacific tropical cyclones before the strongest subtropical jet day, decaying afterwards. In fact, 135 of the 200 strong jet days are associated with at least one tropical cyclone, and 207 tropical cyclones are present on 135 strong tropical jet days, subtropical jet days, or about 1.5 TC per event. And about, not shown here, about 70% of these TCs undergo recurvature and ET. Now, if we look more specifically at the recurving TC jet interaction through here, as the PC recurves, PV is a solid contours. We tend to diabatically outflow tends to amplify the ridge and intensify the jet streak. The irrotational wind vectors are plotted in here. The ones that are in red are just emphasized to show that they're advecting lower values of PV to the northwest. If you do this calculation over a 15 by 15 box and a 48-hour period through here, the advection of PV by the irrotational wind, and that's the moisture flow. So let's watch what happens when you do this. 500 millibar ascent is in green. If now we actually contour what the PV advection by the irrotational wind is, that's the dashed red areas, and here's the maximum right here. And now you superimpose that, the jet streak, and what you see then the advection of lower values of PV by the irrotational wind is what's helping to tighten the PV gradient in here, and that's one of the connections between the recurving TC and the strong subtropical jet that develops downstream of that. And that's a composite with 54 events. And then if you then look what happens in the composite after T0, you can see you get a Rossby wave train, that's just 36 hours, that then propagates downstream towards North America where meteorological mischief can then occur. And the last piece, comparison with the Cleveland superbomb of 1978, makes for an interesting comparison because you see the October storm here on the left, single jet, subtropical jet, whereas the Cleveland superbomb was a coupled jet and much more baroclinicity in through here. The height field is in black, the wind speeds are shaded, and 250 temperatures are in red. Now look at 850. These are standardized anomalies in through here. No cold air in the October storm. Lots of cold air, 2 and 3 sigma standard anomalies in the Cleveland superbomb. And so what that says, then, if we just put this into conclusion, in October 2010 storm, the strong Pacific jet developed from a juxtaposition of TC and TD-related warm pools and trough-related cold pools, which were advected eastward. So you have the cold air disturbances coming out of Asia and warm air masses coming out of the tropics associated with recurving TCs. The TC-TD-related diabatic outflows strengthened the PV gradient and subtropical jet eastward across the North Pacific, and the subtropical jet entrance and exit region dynamics governed the structure and evolution of the surface cyclone from the East Pacific west. Strong jet streams over the North Pacific then occur in association with tropical and polar disturbances, and the recurving jet TC interactions can induce significant downstream flow anomalies in high-impact weather. I want to make one final point by going backwards in through here, and you look at this situation in through here. One could ask the question, from a climate sense in a future climate, whether we're going to see more disturbances that look like this, driven by subtropical jet with relatively small baroclinicity at low levels, as opposed to classic coupled jet patterns associated with amplified baroclinicity in the lower part of the troposphere. So to me, the subtropical jet is the traffic cop of the atmosphere, and that really, I think, needs to be understood in terms of all its variability on intraseasonal time to get some of these things correct. Okay, done.
Okay, thanks a lot, Lance. That was very interesting, compelling meteorological story. Our next speaker is Rong Fu. Rong, are you on the line?
Yeah, I am. I'm sorry. Yeah, I'm on the line.
Okay, great. So what we're going to do is, since we weren't able to test the connection beforehand, I'm going to just present your slides from here.
Oh.
And you can tell me when to advance through them.
Okay.
You'll just have to give me a moment. What I'm going to do is just bring your slides up on our screen here.
Yeah, okay.
And you're logged into the WebEx, right?
Yes.
Okay, good. So you can see my desktop right now?
Yeah. I think, okay, that's a little different from mine, but that's fine.
Okay, so can you see your first slide?
Yeah, I can.
Okay, great. So just let me know when you'd like me to advance to the next slide.
Okay. Should I talk to telephone?
Yeah, yes.
Okay. So my presentation is about the other end of the stream, which is the dry, and I would like to present some preliminary results, explore predictability of the severe to exceptional drought in Texas. And the work I presented here are mainly done by Nilan Fernando. She is a UCA-based postdoc, and she's working with me and also the Texas Water Development Board. And also by Lei Yin, she is a second-year graduate student. Next slide. And 2011 Texas drought is the worst single-year drought recorded in Texas history. And so far, the estimated agriculture loss is more than $7 billion. And the fire has claimed 30 million acres of land and 1,900 homes, and causing 10 people die, including 4 firefighters. And in short, it's absolutely devastating for Texas. Next slide. And the question is, how did the 2011 drought evolve into the worst single-year drought in history? And these four panels shows the data from U.S. Drought Monitor. And as you can see from the top left panel, that's March 15th. And this 2011 drought starts from the fall of 2010 and lasts through winter. by early spring, it looks like just another drought, and water resource management actually committed their non-essential use of water. However, by later spring in April, and the drought suddenly intensified, and by summer, as you can see from two bottom panels, June and August, and the exceptional drought covered most of Texas. Next slide. And how well this drought was predicted. And these four panels shows the CFS most likely prediction. And the top left panel shows the soil anomaly used to initialize the prediction starting from April 2011. And so April, you see soil moisture deficit and indicate the drought. But the prediction shows in summer, for example, June and August, the drought pretty much dissipated and recovered. So this couldn't be further away from the truth. And we also look at CFS, the full ensemble prediction, as well as EPS ensemble prediction. All of them behave similar to the CFS most likely prediction, basically missed the drought of 2011. Next slide, please. What caused the worst one-year drought? Why drought suddenly worsened in later spring and the summer? And we first look at the ENSO Nino index, and the three green, blue contour shows Nino 3, Nino 4, and Nino 3 and 4. As you can see that during the fall of 2010 and the winter of 2011, we had the La Nina. However, the La Nina actually gradually become neutral in spring and summer of 2011. And I think the prediction of dissipating drought is consistent with this. And what about AMO? The blue bar there shows the AMO index. And as you can see that AMO is only mild positive during the spring and the summer of 2011. So bottom line is the La Nina and the AMO are not particularly strong, and they do not seem to be able to explain this rapidly worsening of the drought in 2011. Next slide, please. And so what caused the severe to exceptional drought in Texas? And to explore this question, we look at the 20th century real analysis starting from, for about more than 100 years, starting from 1895. And the results suggest that, first of all, severe to worse drought require persistent rainfall deficits from winter through spring to summer. And among these 18 of these severe extreme drought, 16 of them actually show this persistent rainfall deficits. And when we look at the four worst summer droughts in Texas during the last 100 years, they are 1918, 1935, 1956, and 2011. All of these extreme droughts are contributed by rainfall deficits in spring. So here in this figure, you can see that this yellowish bar indicates March to May standardized rainfall anomalies, and origin bar indicate summer GGA standardized rainfall anomalies, and the blue curve here represents the SPI index. It's a 12-month SPI index, and the origin curve represents palm drought severity index. So the four strongest droughts are indicated by these red arrows. Next slide, please. So how can spring drought intensify summer drought in Texas? Is this an empirical link physically reasonable? Based on Mian and Nielsen Gamma 2010 Journal of Climate paper, and they look at the cause of summer rainfall deficits over Texas. What they found is the most important contributor is a higher convective inhibition energy. And this higher convective inhibition energy seen is due to soil moisture feedback, mainly the surface dryness, and also due to increase of cap inversion. And this cap inversion is strengthened by westerly advection of warm air from the Mexican plateau to the west. And enhanced upper level anticyclonic flow is also an important circulation feature for the summer drought. They can reduce the synoptic disturbance. The question is, could spring rainfall deficits initiate a positive soil moisture feedback and contribute to severe to exceptional summer drought over Texas? If so, could we identify the anomalous large-scale circulation patterns preferred by strong spring rainfall deficits? Is this anomalous pattern predictable? Next slide. So to explore this question, we plotted the seasonal cycle of a convective inhibition energy as shown by panel to your left and the lower panel. And in this panel, the blue curve, solid blue curve, represents the convective inhibition energy from winter to summer to fall for the non-drought year. So as you can see that from winter to spring to summer, the convective inhibition energy gradually decreases in a non-drought year. This gave rise to a higher probability or increase of probability of thermodynamic-driven convection over Texas. And the dashed blue curve here shows the mean thinning evolution, seasonal evolution of the mean thin for the old drought year. So you can see the thinning actually, instead of a persistently gradually decrease from winter to summer, and during the drought year, the thin in later spring and the early summer, and during the summer, the thin is significantly larger than the non-drought year. And the red curve shows the thinning for 2011, and you can actually see a sharp increase of thinning in later spring. The bottom axis shows the pentate. So around 30, that's late April, early May. And you can see, and this increase is actually more than twice as large as the average drought year. And the origin curve shows the seasonal evolution of the thin for the three other strongest drought, which they are 1918, 1925, and 1955. So they also show abnormally large increase of the thin during the spring, prior to the summer drought. So what caused this sharp increase of convective inhibition energy in spring, which subsequently seem to set the positive soil moisture feedback and contribute to severe drought? We look at, based on the Min and the Nielsen's work, and they indicate that westerly advection of the warm temperature from higher elevation from the west contribute to cap inversion. And we actually look at this bottom right panel shows the potential temperature as a contour and the shade, and also the wind for April 2011. As you can see, first of all, the temperature the spring is abnormally hot, especially over the Mexican plateau and also to the west of Texas. And also there is a westerly wind dominant the low-level wind pattern. And normally in April, we would see easterly wind instead of a westerly wind. And so this westerly wind advects the higher temperature as well as potential temperature from west to central and east Texas. as you can see from the top right panel, which shows the potential temperature anomalies, and you can actually see an increase of potential temperature in the lower troposphere throughout the Texas. So this suggests that abnormally strong westerly wind, and also the abnormally higher temperature to the west of Texas, leading to very strong advection of the high temperature and the potential temperature, which increase cap inversion and contribute to large increase of SIN in spring. Next slide.
Hi, Rong, you have about 2 minutes left.
Okay, yeah. Let me skip. So what I want to say is this westerly wind pattern, anomalous wind pattern in spring, is very well correlated with a large-scale geopotential pattern, and that which is also significantly correlated with Nino index in spring. Next slide. And this figure shows if we use observed empirical relationship, we can actually hindcast the above normal westerly wind, which in spring, using the Nino 4 index in February, and this figure is to use to demonstrate potential predictability. Next slide. And this figure shows the CFS V2 most likely forecast actually also predict above normal westerly wind for the 2011, even though they fail to predict the soil moisture deficit associated with summer drought. Next slide.
All right.
And however, the CFS, the full ensemble forecast, did not capture this above normal westerly wind. In fact, in the spring of 2011, in fact, they predict below normal westerly wind. Next slide. And we also look at how well CMIP 5 historical run, how well they represent this zonal wind over the in spring over Texas. And the mean wind is they underestimated the mean wind most model except for UKMO. I'm sorry, except for Hadley Gem. And also we compared the zonal wind for the top 5% of drought, and the pattern, there's some similarity in the pattern, zonal wind pattern. Next slide. This is my second last. So we also look at the relationship between the zonal wind at 850 millibar and the Nino index. And among the 7 models we evaluate, the Hadley Gem is the only model that actually captures the relationship between zonal wind and ENSO in spring. And however, it does not capture the relationship between rainfall and the Nino index. In fact, almost none of the models we evaluate adequately capture the relationship between Texas rainfall and Nino index. Next slide. So summary, the observation, our observation analysis suggests a strong increase of SIN due to westerly advection of the warm temperature, and the surface dryness appear to contribute to 2011 exceptional drought, and the other 3 strongest drought in Texas during past century. This westerly anomaly is correlated to and potentially predictable based on the ENSO index in early spring. Why CFS V2 full ensemble and the most likely ensemble forecast failed to predict the soil moisture deficit during the 2011 summer drought. And these predictions, at least the most likely ensemble forecast, appear to capture the above normal westerly wind at the 850 millibar in spring. We also explored other, we're exploring errors that contribute to these rainfall error in the rainfall anomalies. And finally, based on the historical run of 7 selected CMIP 5, game appear to adequately capture the relationship between Nino index and 850 millibar wind anomaly over Texas in spring, although it failed to capture the observed relationship between Nino index and rainfall anomaly over Texas for the same season. All other six selected CMIM-5 model underestimate the zonal wind over central southwest in spring and how to capture the relationship between rainfall anomaly, low-level wind over Texas, and Nino index. Thank you.
Okay, thanks a lot, Rong. Our last speaker is Upmanu Lall. Upmanu, are you on the phone? Upmanu, are you there?
Yes, I'm there. Sorry, I had the mute on and couldn't figure out how to unmute it.
Yeah, it's taken me quite a bit of time sometimes also. So what I'm going to do is switch control over to you right now.
Okay, so this talk is with several collaborators, Jenny Nakamura, Yochanan Kushner, Richard Seeger, Andy Robertson, Mengshang Liu, and myself. Can you hear?
Yeah, we can hear you, but you're going to have to click Share My Desktop so that we can see your slides.
Oh, okay. All right, just a second.
Yeah, sure. Just switch over into the WebEx software.
Got it.
Okay, great.
Okay.
And if you wouldn't mind maximizing the view, it's right below where your cursor is. You press that button.
Right. Here we go.
Okay, great.
Okay.
Thanks a lot.
Yeah. So I just identified my collaborators, and I wanted to point out that almost all the results that you will see were developed by Jenny Nakamura and Andy Robertson, and they are generally going to be identified. This work started some time back, and I'm a hydrologist, and my interest in this topic was that in many of the diagnostic analyses we had done, we were finding that extreme floods, extreme here being something which is larger than a 10-year flood, seem to be invariably, in the United States at least, associated with tropical moisture exports into that area rather than local convection. So we started looking at, what is the structure of these, and is there any predictability? So that's basically the story that we'll develop in this talk. So starting from the way people typically think of floods, they're thought of as random events which represent the convolution between antecedent soil moisture, which is really past rainfall. And in the case of mid-latitude extreme floods, people generally agree that these correspond to persistent rainfall events with basin scale coverage, at least for large drainage basins. So the question that comes then is that are tropical moisture exports associated with strong persistent circulation anomalies, which some people are calling atmospheric rivers, what role do they play? And are these synoptic weather systems which are modulated by larger scale dynamics, and if so, how? So that's basically the story we've been looking at. And what I'm going to present today is an analysis of flood events which are larger than the 10-year return period in the Ohio River Basin, partly because we've been working on this for a few years before last year's floods in the basin, and also because this area was not one I'd originally thought would correspond to this kind of a feature. We've done this work looking also over France, Germany, the UK, Brazil, and India, but today we'll just focus on the Ohio River Basin. So what we'll do is we'll look at some event attributes for the 2011 floods in the Ohio River Basin, and actually the analysis of composites of past floods which date back to 1903 had been largely done before this flood happened. So it was kind of interesting to see what transpired and to see that it was very similar. So the data sources that we are using for this particular analysis are the COMPO reanalysis data set and the USGS streamflow data set, and also the NCEP reanalysis for 2011. So what we do is we look for evidence of consistent patterns in different variables and organization across events, which perhaps suggests that there might be potential predictability not necessarily in the sense that we are going to predict them a season ahead or anything, but to look for examples of whether these are truly random events or there is sufficient structure associated with them that they may be predictable, conditional on certain observations. And this is at the synoptic scale by and large. And then we look for whether there are circulation types or hidden states that could be possibly related to low frequency variability that give you longer term predictability. So that's sort of the idea. So let's start out with a look at the basin. What is this? Okay, go away. Sorry about that. Okay, here we are. So, so the idea here is that this is the precip for 20 events that are individually larger than the 10-year event in different subbasins. So these are the subbasins of the Ohio River, and this is what happens in last year's April. And what you can see from this is that this precipitation field is a rather large-scale field. It's not limited to just that particular basin. And this is averaged over 9 days of precipitation. So if we look at the incidence of prior events, you see that these are not randomly distributed in time over the last century either. They seem to come clustered, and so the question then arises whether that sort of clustering is due to larger scale controls or low frequency controls on the circulation patterns that are associated with this. So if we look at the evolution of these events, so what you are seeing in this graphic are a sequence of variables. Let's say we focus primarily on precipitation to begin with, which is right in the top left. So the solid line that you're seeing here that's black is the April 2011 event, traced back 10 days from the peak. The peak is, when the peak occurs, is day 0, and then we go 2 days beyond and 10 days prior to that. And then the solid gray line you're seeing is the mean of the 20 prior events that we just saw on the previous slide. The dashed line is the median, and the gray shaded area is the 25th, 75th percentile. So what you see for the 2011 event is actually representative of individual events where there's a period of rainfall, there's a lull, there's a period of rainfall, a minor lull, and a period of rainfall, suggestive that there are perhaps waves of moisture coming in that are driven by some similar phenomena. Let's stay with this idea and then jump down to integrated moisture convergence into the region or the meridional moisture flux, and you see the point that I was just making emphasized one more time. So we'll visit some of the other fields later, so I won't say more about them at the moment. So here's an example of the circulation patterns associated with the 20 event composites over 9 days preceding the event. So each event is synchronized to its peak, and then you look back 9 days. So for the April 27 event, this is the circulation field. This is the moisture divergence or source and from the surface, and that's where the moisture convergence is happening in terms of vertical velocities. So, and these are the anomalies associated with the climatology, associated with days in March, April, May. So this is pretty much what you would expect for an event that goes through synoptically. This is a little bit of a surprise in that when you average 20 randomly chosen flood events, randomly only in that they exceeded the nominal 10-year event estimated from the period of record, and you average them, you still see structures which are very similar to what you see for an individual event. And in fact, if you look event by event, the features are very similar. There are slight spatial temporal shifts which smooth that picture out relative to the event-based picture. So that's kind of interesting here. So then if we look at a Hofmuller diagram as to how these events evolve, this is the 20 event composite, and this is the 27 April 2011 event. And what you are looking at is the moisture, meridional moisture transport in colors, and the meridional wind associated with the contours crossing 25 north in this particular picture. And what you see basically is that between the Rockies and the Appalachians, there is essentially a waveguide that is forming, that is moving this moisture through. And if we go to the same picture for 35 degrees north in terms of what fluxes cross there, you see that that picture is enhanced still. And we see this kind of a feature fairly regularly in most of the analyses we have done, where the fluxes that are going through are anomalously stronger in the 25 to 35 band, or as you cross 35 as compared to the lower ones. The moisture source, of course, is coming from below 25 associated with these. So if we look at how these things parse out, the question is, if you partition these in terms of whether this is a moisture anomaly times climatological wind, or circulation anomaly times the climatological moisture, or the moisture anomaly times the circulation anomaly, the pictures that emerge are what you see here. On the left are the composites of the 20 events, and on the right is the 2011 event. And one caveat that I would throw out here is that in terms of the way these systems are stimulated, obviously if the wind goes to zero, there is no game. So we do expect the circulation anomaly to be driving the system, and indeed we see that in the composite relative to the moisture anomaly, and in the event itself relative to the moisture anomaly, the circulation anomaly product with the moisture dominates this particular picture. So that's basically the idea then develops as to what are the aspects of the circulation that may be interesting here in terms of driving these sort of events. So we take a look at that, and here what we are looking at is sea level, the 700 millibar geopotential height anomalies and the vertical pressure velocity in colors, looking back from day -9 to day -1 of the flood events. And again, we have the 20 event average on the left and the April 2011 event on the right. And the basic feature that emerges is that there is a dipole-like structure which varies to some extent in terms of its spatial manifestation, but it is established as far back as day -9 and moves forward. And we can see it enlarged here. So what you see for the event is that there is a high pressure system and a low pressure system that emerges. This is the location of the basin. So the circulation patterns that we were seeing earlier come through is basically an anticyclonic feature that then develops around this high and its extension over into this area. So this is one of the features that emerges. There's a few others as well. But if we take that particular dipole and composite it and also look at the events going back all the way, back now to 60 days, you start seeing hints of a quasi-periodic structure that goes quite a bit back with respect to the structure of that dipole. And if we then do a spectral analysis on it, we see that that particular dipole's time series then partitions into that wave-like structure, and down here we see that a variety of periods are represented, and the question that emerges is, what is the structure that is driving these particular features? So we haven't quite finished that analysis yet in terms of nailing that down, but still it's interesting to observe this. And what we have done is look at whether there are circulation types and their structure that can inform these wave-like patterns. So this analysis is done now by Andy Robertson on 700 hectopascal geopotential heights covering this particular domain. The bounds, exact bounds are identified there. So he does that analysis for March, April, May, which is the flood season we are looking at predominantly. And he does first principal components, and then he does a k-means cluster analysis using those three principal components and identifies 7 clusters. So there are some features here that are worth looking at. For example, in cluster 1, what you're seeing is that sort of a dipole structure that we were looking at and the anticyclonic flow associated with it. In cluster 2, we have a shifted pattern associated with the dipole, and similarly in 3 and 4. But in 3, the pattern is a cyclonic flow, and it's kind of reversed in terms of the structure. Cluster 5 is a strong cyclonic structure with a low located there, and then 6 is also a cyclonic structure, and 7 is a little bit of an anticyclone. So these are the patterns that come out. The question is, how do these relate to the floods? So if you go and look at the 10-year return period floods that we have in the database and their association on days associated with flooding, then we see that cluster 4, which had anticyclonic features similar to what we were looking at, and cluster 2 show up with counts that are statistically significant based on a bootstrap. 3, 6, 7, and 1 are also showing up. These are all anticyclonic patterns for the most part, and 7 also is statistically significant, even though its count is small, but its overall frequency of occurring is small. What's interesting is cluster 5, which has a strong cyclonic structure, ends up with no flood days at all. So let's see how these shape up for 2011. Incidentally, the previous analysis did not include the 2011 data, and what we see is here's flood days. Cluster 4 shows up there. Cluster 2 shows up in the other flood days. Cluster 2 shows up in these flood days, and also 3. So it's kind of interesting. And then on the days that are not flooding, if you look through here, there's few cases of cluster 5, but in this year that's not particularly prominent. How do these clusters relate to ENSO sort of variability? There's papers by prior investigators, Wayne Higgins, for example, which point to increased rainfall in the Midwest in March, April, May during La Nina events, and we see that consistent with what we are seeing so far, clusters 4, 2, and 7, and 3, 6, 1 are the ones that are the most common flooding ones. Out of those, 4, 2 do correspond to La Nina, as well as 6 and 3, and then 5, 7, 1 correspond to El Nino. And during 2011, the La Nina conditions that were prevalent could possibly then have had something to do with this. Similarly, Andy's done this analysis with MJO phases, and he notes that for the circulation type 4, which is implicated in flooding situations, the MJO phase 5 is persistent for about the first 6 days before the flood, and then phase 3 is persistent for the days 7 through 14 before the flood. And similarly for cluster type 5, when floods don't happen, this MJO phase 8 is persistent for all 14 days. And similarly, there are some other features. So the idea here is that perhaps there are some relationships here which are meaningful in terms of analyzing these features and coming up with predictive models. So that brings me quickly to my summary. Our analyses so far suggest, with the Ohio River Basin and with the other analyses that we have done in other locations, that when you get to these extreme floods, the amount of water that needs to be delivered is usually quite large and is hence not coming from local sources. And similarly, the antecedent conditions that have to develop with soil moisture require some sort of persistent mechanisms for bringing moisture in, and we see that these are there. And our thoughts are that in terms of looking at climate change scenarios for floods or even seasonal simulations, it is important to understand the circulation features and the drivers of those circulation features that deliver these kind of floods, and to compare them in the GCMs in historical runs and see if those are well represented as a precursor to looking forward. Second, these tropical Atlantic moisture sources and the associated circulation patterns are usually implicated for meridional moisture transport into all of the red regions that are listed there. And that suggests that for these extreme events, there may be a possibility of detecting these and doing something with them fairly robustly. In the Nippers and Wernley tropical moisture export analysis, they note that there are only about 4 moisture source regions that are contributing fluxes for meridional transport in a consistent way almost all the time. And the question then comes, how does a circulation interact with these sources to deliver moisture to different places and lead to flood or lack of flood incidents there? Third, we notice that the circulation mechanisms extended in time do show wave-like structures of different wave numbers, and those in turn may be related to circulation forcing by tropical heating or by other sources. So we need to do some work to identify those. And independent of these, we are working on short to medium range probabilistic forecasts of these events, looking 5 days ahead, 15 days ahead as initial value problems, and looking for seasonal and climate change simulations through stochastic models that are multi-layer models. So with that, I will stop at this point and see if there are questions.
Okay, thanks a lot, Upmanu. It's a little bit after 2 o'clock, so if anyone has an appointment in the room or on the line that they need to get to, feel free to head out at this point. But the speakers, I believe, are all able to stay on the line for at least 10 more minutes, so we'd like to have a question session right now. So are there any questions here in the room for any of the speakers today? Okay, any questions? Oh, sorry, Rick. Yeah.
Rick Rosen, Kerry, Emanuel. Kerry, I was struck by that picture from a recent Nature article with the U.S. down into the tropical Atlantic. I'm curious what role, if any, Saharan dust played in your thinking. The role of that dust has been debated on and off.
Can everyone hear me?
Yep.
Okay. I think I got most of that question, Rick. That's an interesting question about Saharan dust. There's been a lot of research on this. There's a direct effect, maybe, on the microphysics of what's going on in tropical cyclones, and then there's the indirect effect of it actually intercepting some solar radiation and cooling the sea. I'm not sure about that indirect effect, and I must admit I don't really know the answer to that. From what I've read of that, it seems to be a smaller effect than the sulfate aerosols that persists through much larger part of the year.
Thank you, Kerry. And if I may, one other question for Chunzai. The results you showed were very interesting at the size of the worm pool, but there seemed to be two effects. You demonstrated that when you have the large worm pool, there is a smaller percentage of storms that will make landfall, but on the other hand, the competing there are a lot more tropical storms. And I thought I saw in one of your slides that the absolute number of landfalling storms may actually be stronger, may be larger, even with a larger warm pool. I may have seen that. I think when you were comparing the 10 strongest and 10 weakest. So your result seemed very interesting about the lower percentage, but I wondered to what extent that's counteracted by just a large number of storms, so that in the end there are more landfalling storms. Or did I get something wrong there?
Yes, you are right. Yes, actually, answer to your question, you are right. For large worm pool has two effects. One is increase the total number of hurricanes, and the second one is if you have a large worm pool, the worm pool induces atmospheric circulation, which is unfavorable for hurricane to make landfall in the U.S. Also, another question here is that the landfall activity also dependent on so many other stuff like the storm internal dynamic and the short and the weather pattern. So you are right. So the total number is increased. However, the landfall number is decreased.
Are there any questions on the phone line? Any other questions in the room here? Okay, well, thanks again to all of our speakers. A lot to think about from these talks. The final MAP webinar is taking place next month, May 2nd. It's going to be on the topic of the 5th phase of the coupled model intercomparison project, and we have 5 speakers again for that. We have Justin Sheffield from Princeton, Yolande Serra from University of Arizona, Jinyi Jin from UC Irvine, Dave Nealon from UCLA, and Tao Zhang from the Earth System Research Laboratory. And it'll also start at 12:30 p.m., but it's the first Tuesday of the month as opposed to the second Tuesday of the month, which is our regular schedule. So thanks everyone for joining. Thanks again to our speakers, and we'll talk to you next month. Bye.